Today's video is going to start with introducing us to our next AP topic, which is going to be about integrals and net change. And so what we're going to do first is just a little warm-up to get used to kind of what's happening when we start integrating our rate functions. So this is going to be a little bit different from what we've done before. So for these problems, actually 1 through 4, what we're supposed to do is write a sentence including appropriate units of measure. So here we go. So the first problem tells us that W prime of t is the rate of growth of a child in pounds per year. And so that's going to be a signature of these problems. The function that they're giving us is going to be a rate function. So in this case, it's the rate of a growth of a child in pounds per year. That's going to be important. And so what we need to answer is, what does the integral from 5 to 10 of W prime of t dt represent? So the first thing we're going to kind of work through is, what would be the units if I integrate this rate function? So we know that integrating is really taking the area of our integral. So if I think of it that way, I know the units of my rate function are going to be pounds per year. Okay, so those are my y values of the function. They're giving me the rate in pounds per year. Now, I'm going to multiply that kind of by my x values, which are right here, and those are going to be in years. Okay, so what we're really imagining here is kind of a function here, right? If I knew, let's say, what this function looked like, and I'm just sketching something. Let's say this was W prime of t, right? We know that our y-axis is pounds per year, and our x-axis here would be in years. So that's kind of what I'm representing here. So if we were to take the area, we'd be multiplying these units, and what we noticed happen is those years would cancel out, and so our units would be pounds. So if I integrate that rate function, what I'm getting is units in pounds. So that's going to help me answer the question. Our question was, what does 5 to 10, the integral from 5 to 10 of W prime of t dt represent? Well, that means that the integral from 5 to 10 of W prime of t dt represents, well, if the units of that integral are in pounds, that must be telling me then it represents the growth of the child in pounds. And then we want to be sure to specify the time period. So it represents the growth of the child in pounds over the time period t equals 5 to t equals 10 years. And you guys have actually written explanations like this. If you think back to when we were doing Riemann sums and we had to write what that integral represented. So the same things are going to be important now that were then before. So you want to tell what it represents. Here it's the growth of the child. You want to specify the units. And then you want to specify the exact time period with units. So that would be a complete answer to answer what that integral represents. So let's look at some more. So the next one, if oil leaks from a tank at a rate, again, we have a rate, and here they're just giving us a function R of t. Our units are gallons per minute, and so we want to know, what does this integral represent? So again, what I'm thinking is my y values are gallons per minute. My x values here are going to be in minutes, so my units must be gallons. So now I know that the integral from 0 to 120 of R of t dt represents, sorry about that mess there, represents the amount of oil in gallons that leak from the tank over the time period from t equals 0 to t equals 120 minutes. Okay, now for number 3, we've added something a little bit new here. So we have a honeybee population starts with 100 bees. So we have some initial value here, which we haven't really seen in the other problems. Okay, so it starts with 100 bees and then increases at a rate of n prime of t bees per week. So there's that integral, that rate function. Okay, so n prime of t bees per week. So what does 100 plus the integral from 0 to 15 of n prime of t dt represent? Well, let's kind of break this up. We know that 100 was the initial number of bees in the population. So I'm going to recopy this here. Okay, so we said 100 was the starting number of bees. Now, my rate, let's see, this is the bees per week times the number of bees. So this would be the amount of bees added to the population. My integral is going to give us the number of bees added to the population. So it tells me how many bees that population increased by. So then that whole expression, 100 plus the integral from 0 to 15 of n prime of t dt, is going to represent the actual population size at t equals 15 weeks. So now we're not just talking about how many bees the population increased by, we actually have the population size, that total population size at time t equals 15 weeks. All right, last one, working with units again. So we have if the units for x are feet and the units for mx are pounds for foot, what are the units for dm dx? So let's take a look at that first. So dm dx, so the rate of change of m with respect to x. Well, we said m, our units are pounds per foot, and the units for x are feet. So our units there are going to be pounds per square foot. Now, on the other hand, if I'm integrating from 2 to 8 of m of x dx, our units are going to be, in this case, pounds per feet. And now we're doing times feet, so in this case, our units are going to be pounds. So again, the purpose here is just to get us comfortable with what's happening to these units when we're integrating these rate functions. All right, so let's start looking at some problems. Now, here's the key to all of these problems. In general, if I integrate a rate function, that's going to give me the net change. So if we think back here, think back to example 1, when I integrated that rate of growth, I got the change in that child's growth. We got how much he grew over that time period. So integrating a rate function is going to give us the net change. Now, if I have an initial amount, like we did with our bees, and I add the integral of the rate function, Now we're getting the new amount. So we're getting a new total amount because we have an initial amount plus our net change, and that's going to give us our new amount. So this is really the key to these types of problems. So let's go ahead and look at some problems and see how we would set up these accumulation functions to solve these problems. So my first example says for t between 0 and 31, the rate of change of the number of mosquitoes on tropical island at time t days is modeled by this function. So again, the important thing to represent or to notice here is that this function represents a rate. Okay, they're also telling us that there are 1,000 mosquitoes on tropical island at time t equals 0. So here's our initial amount. So part A asks us to set up a function that will allow us to find the net change in the number of mosquitoes between t equals 0 and t equals 5 days. Well, we said to get the net change, we're going to integrate the rate function. So my function is going to be y equals, I know I need to integrate my rate, so I'm integrating m of t dt. And since I want to find the change between t equals 0 and t equals 5, those are going to give me my limits of integration. So there's a function that's going to give me that net change. Now, if I want a function that's going to allow me to find the number of mosquitoes on the island, right, now I want the new amount. So I have to take into consideration that initial amount. Sorry for my trouble speaking today. Okay, so now to get the number of mosquitoes, I know I need my initial amount, which we said was 1,000. And then I'm going to add the integral of my rate function. So plus the integral from 0 to 5 of m of t dt. So that'll give me the new amount. So we have the initial amount of mosquitoes plus how many we added is going to give us that total number. Now, one thing that's going to be important to make sure you check is that your initial condition is going to match your lower limit of integration. So here's what I mean. This said that there were 1,000 mosquitoes at time t equals 0. So this is the amount at t equals 0, which means my integral better have a lower limit of 0 as well, so that my initial condition matches the starting point of my integral. And we'll revisit that as we go through. All right, so let's try another example. So number 2, the rate at which water flows out of a pipe in gallons per hour is given by a differentiable function r of time t. Okay, so here I have my rate function is my function r. The water is flowing out of the pipe into a container that originally contained 115 gallons of water. So that's my initial amount, is my 115 gallons. So part A, I need to set up a function that will allow me to find the net change in the amount of water in the tank. Again, we said net change is given to us by integrating our rate function, which in this case is r of t. I have my dt on my integral, and now I need it from the time interval t equals 0 to t equals 24, so that's going to be from 0 to 24. Okay. Now, I want to set up a function that's going to allow me to find the amount of water, right? My new amount of water in the tank after 24 hours. Okay, so now the amount of water in the tank, the new amount is going to be my initial, which is my 115, plus I'm going to integrate my rate function, which is going to give me the amount of water that was added to that tank from 0 to 24. And again, I do a double check here. It says it originally contained 115 gallons of water, so this initial condition is at time t equals 0, which matches my lower limit of 0. All right. Number 3. Now we're going to take a problem and try to set up these rate functions. But number 3 is going to be a little more challenging because obviously we have a couple of things going on here. So we have the rate at which people enter an amusement park on a given day is modeled by the function e. So I have this as a rate function. I also know the rate at which people leave the amusement park on the same day, and that's given to me by this. So in this case, I have 2 rate functions. It's telling me that both my rate functions are measured in people per hour, and time is measured in hours after midnight. Okay, so the functions are valid for t between 9 and 23. So in terms of this problem, if my time is valid for between 9 and 23, essentially that's telling me that the park is open between 9 a.m. and 11 at night. Okay, so at time t equals 9, there are no people in the park, right? This is telling me that my initial amount is 0. Okay, so I know I've got 2 rate functions, I know the units for both of those functions, and I know my initial amount is 0. So part A is asking us to set up a function that will allow us to find how many people enter the park by 5 p.m. Okay, so it's not asking me how many people are in the park, it's only asking me how many people have entered. So that's telling me that I need to integrate my function e of t dt. Okay, now for my limits. I know my lower limit has to be 9. The park isn't open before then. Now, by 5 o'clock p.m., that's 8 hours later, so that gives me an upper limit of 17. So the integral from 9 to 17 of e of t dt is going to tell me how many people enter the park by 5 p.m. Okay, part B, the price of admission to the park is $15 until 5 p.m. And after 5 p.m. it gives the price of admission as $11. So we need to calculate now how many dollars are collected on the given day. So obviously the amount of money collected just depends on the people coming into the park. We're still not worried about who's leaving, we just want to know who came in. So now I know I'm going to have $15 times the amount of people who entered the park by 5. Well, that was our 9 to 17 of e of t dt. Plus, I'm going to be adding $11 times the amount of people who entered between 5 o'clock and when the park closed at 11 p.m. So 17 to 23 of e of t dt. So that's going to give me how much money I collected on that day. All right, now we want to pull some of this together. So now we need to set up a function that's going to allow us to find how many people are in the park at 5 o'clock p.m. So before I set up a function, I just want to think about this. If I want to know how many people are in the park, I need to consider the initial amount, how many were in the park when it opened, plus I need to add how many entered, and I'm going to subtract the number of people that left. So let's think about this, and we can go back to our information. We know that it told us, let's see, when the park opened at time t equals 9, there were no people in the park. So this amount is just going to be 0. How many entered? Well, we know that's going to be given to us by the integral from 9 to 17, again from the hours of 9 to 5. And we're going to integrate our e of t dt. And then we're going to subtract the integral from 9 to 17 of L of t dt. That's telling us how many people left the park. Now, obviously then we don't need to worry about the 0. One thing I do want to point out, however, is going back here, it said at time t equals 0, t equals 9, there are no people in the park. So this 0 corresponds to the time t equals 9, which matches our lower limit, which we said it had to. So that's always worth double checking. Does your initial amount match the time for your lower limit of integration? Now, I can simplify this. Obviously, we don't need to take into account the 0. And I can simplify this integral, just rewriting it as 9 to 17 of e of t minus L of t dt. So that's telling me how many people are in the park at 5 p.m. So now, if I look at part D, it says in the context of this problem, what does the integral from 9 to 17 of e of t minus L of t dt equals 3,725 represent? Well, we just set up that integral and said it told us how many people are in the park at 5. So now we know that 3,725 people are in the park at 5 p.m. Okay. Let's go ahead and do one more problem. Again, I know this is a long video, but we'll do one more and then we'll have the opportunity to work through a bunch in class tomorrow. All right, so here is our mosquito problem. So it's telling us between the time of 0 and 31, the rate of change of the number of mosquitoes on Tropical Island at time t days is modeled by this function. So here is my rate function, and that's in mosquitoes per day. They're also telling us that we have 1,000 mosquitoes on the island at t equals 0. So that's our initial amount. So for part A, it says, show that the number of mosquitoes on Tropical Island is increasing at time t equals 6. Well, if the number of mosquitoes is increasing, that must mean that the rate is greater than 0 at time t equals 6. So to show that I have that rate function, all I'm going to do is I'm going to calculate m of 6. I'm going to calculate that rate and show that it's greater than 0. So here's where our calculator is going to come in handy. I have 5 times the square root of 6 times cosine of 6 divided by 5. So we do get a positive rate here. So m of 6 is approximately 4.438, which is greater than 0. So I'm just going to say since m of 6 is greater than 0, the number of mosquitoes is increasing at time t equals 6. Okay, part B, we need to set up an integral to determine the net change, right, in the mosquito population on the island for time between 0 and 31 days. And we're going to round our answer to the nearest whole number. Again, we said net change is given to us by integrating our rate function. So we're going to integrate m of t dt from 0 to 31. And again, we're going to use our calculator to do that. So let's see, now we're integrating from 0 to 31. We've got 5 times the square root of x times cosine of x divided by 5 dx let's see what we get. All right, so we get, let's see, rounding our answer to the nearest whole number, it's approximately negative 36. So what that's telling me, since it's negative, is that over that time period, the number of mosquitoes has actually gone down. Okay, and then the last piece here, how many mosquitoes will be on the island at time t equals 31? Again, to get this, how many mosquitoes, we need to consider our initial amount plus the integral of our rate function. So that's going to give us the initial amount plus the net change. So my initial amount at time 0, we said was 1,000, plus we're going to integrate from 0 to 31. Again, my net amount was at time t equals 0, so my lower limit also needs to be 0. So 0 to 31 of m of t dt. Well, we already calculated this as 36, so we know the population is going to be 964 mosquitoes. Okay, so that's a first look at our net change, integrals and net change problems. We'll do some practice tomorrow, and then you'll have another video which will delve into some more AP problems.